Okay, so let's see the contents first. First, I will explain about the wavelets which are used for the two-dimensional signals, images, and then I will show you that how you can use the filter banks to find the wavelet transform, both analysis and synthesis. And then I will explain the Wavelet Analyzer tool of MATLAB by which you can find the wavelet transform of images. And then I will explain the few MATLAB functions such as DWT, IDWT2, WaveBreak and WaveRect2. And then in the last I will make one Simulink model which can perform the wavelet transform of an image. Before watching this video, I recommend you to watch this my previous video. The link is given in the description. This previous video actually explains about the theoretical aspect of the wavelet theory and its applications. So if you go through this video, you will have the better idea about the wavelet transform. Now let's see the what are the wavelets for two-dimensional signals. Actually, our images are two-dimensional data. That means an image f, which is a function of the spatial coordinate x and y. So obviously, to find the wave transform of two-dimensional data, definitely we need the two-dimensional wavelets such as psi xy instead of psi t. Few examples of two-dimensional wavelets are shown here. For example, the 2D Haar wavelet is shown here, and one 2D Mexican hat wavelet is shown. But this approach requires more computational power. That means a lot of computation is needed. So there is another approach which requires a less computational power. So we can apply the one-dimensional transform to the rows and columns of the image successively as separable two-dimensional transform. That means instead of taking the two-dimensional wavelet, we will use the one-dimensional wavelet, and we will perform the row-wise as well as the column-wise operation to get the final two-dimensional transform. And in the most of the applications where the wavelets are used for image processing, this approach is preferred because it needs a low computational complexity, right, for separable transform. Now let's see the filter bank theory. The wavelet decomposition of an image based on the multi-resolution theory can be done using the digital FIR filters. And we have the fast ON algorithm to compute this these wavelet coefficients using filter banks. So as proposed by Mallet, and this is the scheme. So this is the filter bank scheme which is based on the rows and column wise operation. So you can see that this is your image, which is M by M image, and first we do the row wise operation. So LOD is your low pass decomposition filter, and this is HID, high pass wavelet decomposition filter. And then by doing the downsample by 2, we get the data, and then we do the column wise operation, the similar operation. I mean the passing the signal through low pass and high pass wavelet filters, and then doing the downsample by 2. So we get the 4 matrices at the output, which is known as the CA, CH, CV and CD. This CA is known as approximation coefficients, and its size is just half of your image M by M. It is M by 2 by M by 2 because of this downsampling. And this CH actually represent this horizontal detail coefficient, and CV represent the vertical detail coefficients, and CD represents the diagonal detail coefficients. And this is the reverse operation. That means wavelet reconstruction or synthesis. So if you have all these 4 matrices CA, CH, CV and CD, you can get your signal, your image back with the reverse operation. So first you need to upsample by 2 and then passing those signals through the reconstruction filter instead of decomposition filter. These filters are different. And then upsample by 2 again, and where we are doing again the row wise and column wise operation as a separable transform. So combining these we get the M by M image back. So this is your image synthesis, and here you can see with a simple example that this is your image, which is of, let's say, size M by M. After one level of decomposition, you get 4 matrices like this. So this is a CA11, actually denotes the first level of decomposition. So CA matrix at the level 1, and then CH at the level 1, which is horizontal detail coefficients, and then vertical detail coefficients, and then diagonal detail coefficients. So all these matrices are of size M by 2, M by 2. So suppose your image is of size 256 by 256. Here you will get 128 by 128 matrix size. So this is the first level decomposition. Now if you want to the further decomposition, let's say the second level, then we will take this matrix only, the CA1. The CA1 is further decomposed into the 4 parts, which as shown in this image. So here the CA1 matrix, right, is decomposed, which is already of M by 2, M by 2 size. With the same manner, it is decomposed into the 4 matrices CA2, CH2, CV2 and CD2, and these matrices size are M by 4 and then M by 4. And you can do the third level decomposition of CA2 and so on. So you can make a tree. And here one example image is taken. So this is an image of 256 by 256 size, and after the one level of decomposition you can see these matrices. This is your approximation coefficient CA, and these are horizontal coefficients CH, and this is vertical coefficients, and these are diagonal detail coefficients. So you can clearly see that in diagonal detail coefficients, that all diagonal details of image are dominant, while horizontal and vertical coefficients are negligible. And in CH matrix you can see that the horizontal detail of image is highlighted. These coefficients are large in magnitude. Similarly, in vertical matrix, these vertical detail of image is dominant. And if you go for the second level decomposition, this CA matrix will be decomposed further in these 4 matrices again. You can see, so this is your CA2, and you can see that this is horizontal H, this is vertical, and this is diagonal. These are the diagonal coefficients. So you can see that how the wavelets are capable of capturing the horizontal, vertical and the diagonal details available in any image. So that's the strength of wavelet to capture the images. That's why wavelets are used in various pattern recognition applications. And this is one another example image of Lena. Here the one level decomposition is done. So this is your CA matrix, and this is your CH, and this is your CV, and this is CD. So in the CV you can see that this part which has some vertical details, you can see, so this is available in vertical coefficients, while this is missing. Okay, this is missing in horizontal as well as in diagonal. So you can see the strength of wavelet to capture such horizontal, vertical and detail coefficients. And this is the second level decomposition, right? So these details are more prominent here. And again this is the third level decomposition. Okay, so this CA2 is further decomposed in 3 matrices CA3, CH3, and this is CV3, and this is CD3. And now let's see the MATLAB's Wavelet Analyzer tool. Here just see this Wavelet 2D. So when you press this button, you get the facility where you can find the wavelet transform of your images. So let's jump to the MATLAB, and where we can do this operation. So this is my MATLAB. Let me type the Wavelet Analyzer at the command prompt and simply pressing the enter, and this window is open. So here you can find that this is my Wavelet 2D. Just by opening it, you get this window, and now go to the file and load image. It asks to load your image. You can go to your relevant directory, and let's say this is my image. I select this W8 and then open, and let me choose the wavelet. Here you have the freedom to choose various wavelets like RDB, simlet, coeflet, biorthogonal, DMare, reverse biorthogonal, etc. And you can choose the level of decomposition also. So for example, if I choose, let's say, R wavelet and the decomposition level 1, and then just pressing this analyze. Okay, so this wavelet transform is done for this input image. So this is my original image, and these 4 matrices I am getting. This is the CA, this is CH, CV, and CD. So from these coefficient matrices, you can clearly see that in this CH, these horizontal coefficients are more prominent, and here in diagonal, these diagonal coefficients are of high values, and in vertical matrix, these vertical detail is more prominent. And by combining these, the synthesis is also done, which is the inverse discrete wavelet transform. So this is your reconstructed or synthesized image. You can do the second level transform also. Just choose 2 and then press analyze, and you have the second level transform. You can visualize also. For example, if you press this 4, this image becomes bigger. You can see clearly all the details, right? So here you can load your various images, and you can actually see that what happens with those images. So this is another image of pepper, and let's see, I choose a coef 5 wavelet and then second level of decomposition, and then pressing analyze. So this is the second level decomposition of this image, right? So this is about the wavelet tool, which is the ready-made tool you can use. Now let's go back to the presentation. Okay, now we will do the same operation by writing some MATLAB functions. So the first pair is DWT2 and IDWT2 function. So this is actually the single level wavelet decomposition and wavelet reconstruction functions. So this is the syntax. When it executes the DWT2, this X is your image, and here you write the name of the wavelet, and then you need to define the image extension mode. Actually, we need the image extension of the image to treat the boundary problems. Okay, so when you execute this, you get all 4 matrices CA, CH, CV, and CD, and this is just a single level decomposition. So now if you want to do the inverse transform, you just execute IDWT2 and pass all these 4 matrices here, and define the name of wavelet and then signal extension mode, and you will get your signal back, right? So this signal extension mode, actually I have already explained in my few previous videos. You can watch them. These are signal extensions such as zero padding is also there, or the periodic extension, or symmetric extension, etc. There are others modes also. And this is a simple program which utilizes the DWT2 and IDWT2. So in this first line, we are just getting, we are selecting the image, our image. So when you execute this UI get file, the Windows dialog box appears, from where you can select your image file, and then reading its path, etc. And then using this imread, we are reading the image. So all image values, pixel values will be stored in this img. Now converting this img, since it's a grayscale image, so it is of type unsigned integer 8. So now converting this into the double before taking the wavelet transform. And then once DWT2 is executed, we get the 4 matrices CA, CH, CB, and CD. So here we are using the HAR wavelet, and the image extension mode is symmetric. And these are the few plot commands. So these are some plot commands to plot all these matrices. I mean CA, CB, CD, and this is the inverse wavelet transform. That means we have passed all 4 matrices, the name of the wavelet and the signal extension mode, and we get our signal back. So this is our reconstructed image, and this constructed image is also shown here. So let me execute this program in the MATLAB, and let's see what type of output we get there. So let me open the MATLAB, and this program is I have already written to save the time. So let me execute this by pressing this run button. Let me choose my image. Let me choose this Lena, for example. Okay, so I'm getting this is my reconstructed image, and these 4 are actually my CA. This is first the CA approximation coefficients, and this is CH horizontal detail coefficients, and this is vertical detail coefficients, and these are CD diagonal detail coefficients. So here you can see that these vertical elements are more visible in this. So this is how this program can perform and can show you the wavelet coefficient matrices. Okay, let me jump to the presentation. Okay, now let's see the wavelet another functions, the WaveDec2 and WaveRec2. Actually, these functions are the multi-level decomposition and reconstruction signals. In the previous case, they are only a single level decomposition and reconstruction. And suppose you want to take a 3-level decomposition of a particular image. So you have to execute those functions DWT2 3 times. But that is not good to write code, similar code 3 times. So here you can use the WaveDec2 function. You just need to define the level of decompositions. You will get all 3 decomposition levels simultaneously using a single function. So this is the syntax of WaveDec and WaveRec. So in the WaveDec, X is your input, and N, yes, you need to define the level of decomposition. Suppose you want to do the 2-level decomposition, then N will be 2 simply. And W name, you will write the name of the wavelet which you are using to decompose the image X. And as output, you get 2 matrices. One is the C and another is the S. What are these? Although they are called, the C is called as a wavelet coefficient matrix, S is known as a bookkeeping matrix. This is a little bit complex. I will show you that what are these matrices in the next slide. And in the reconstruction, you just pass these 2 matrices C and S here, and then define the name of the wavelet. Simply you will get your reconstructed image Y. Here the now signal extension mode is also needed. So for example, as in the previous case it was passed inside the function, now here it is passed outside the function as this MATLAB command. So before executing these two, you need to execute this function DWT mode, and in mode you will write the name of your extension. For example, if you are using the periodic, in place of mode you will write simply PER like this. So your extension mode will be periodic, right? So let's see what are the C and S matrices. So for n level of decomposition, the matrix C contains all the wavelet coefficients and matrix S contains size of all those matrices as shown below. So here you can see that this is your C matrix. So for n level of decomposition, you can see that the detail coefficient, the vertical coefficient matrix and the horizontal CH1, CV1, CD1 are arranged like this at the first level. After that CD2, CV2 and CH2, and in similar manner all matrices are arranged. So at the last you can see that this is CHN, CVN and CDN. And the last matrix is the approximation coefficient at the level n. And this is your S matrix. This is your S matrix. So in S matrix, you can see that the first row from the bottom is carrying the image size m by m, row and column. And then the second row carries the size of these three matrices, I mean CD1, CV1 and CH1, which is obviously the half m by 2 after the first level. And at the nth level, obviously the size will become the m upon 2 power n, m upon 2 power n. And the CAN will also be of the same size, ma upon 2 power n, m upon 2 power n. So this is actually the S matrix and this is our C matrix. So from these two matrices, if you want to find the detail coefficients or approximation coefficients at a particular level, you need to execute the two different functions, and these two different functions are these two, that is the detcoef2 and the epcoef2. So when you execute this function detcoef2, it will extract the detail coefficients, all the detail coefficients, I mean the CV, CH and CD at a particular demanded level. And if you execute this epcoef2, it will return approximation coefficient matrix at the desired level. Okay, so let's see the syntax. So this is the syntax of detcoef2. So you need to pass these two matrices C and S, right? And then you need to define the label. At what level you want to extract the horizontal, vertical and detail coefficients. So at that level n, this function returns these three matrices H, horizontal, vertical and detail matrices. Similarly, if you want the approximation coefficients at a particular level n, you need to define execute this function fcoef2 like this. So you need to pass this C and S and define the wavelet name. You will get the approximation coefficients at that level. So this is one example program which will use the wavedec2, waverec2, fcoef2 and detcoef2. So let's see. So the first instruction is simple, which is when executed, the system dialog box appear. So you can choose your grayscale image, and then converting the image into the double, you are reading the image here, and then this we are entering from the taking the input from the user, enter the decomposition level. So this will be the prompted at the command prompt. User will enter the value of decomposition level, for example let's say n equal to 2. So there will be the 2 level decomposition. DWT mode is defined before executing the wavedec2, okay, as I said before. So here we are using the periodic extension mode, And now the image img is passed in WaveDAC2 function, and n is your what? It's a decomposition label which is given by the user, and the wavelet I am using here, you can use your own wavelet, whatever you like, and you get the two matrices C and S as the output, right? From the C and S matrix, you can find, you can extract the detailed coefficients, I mean H, V and D at your desired level. So in this, by this function, I am extracting at the last level. So for example, if I give n equal to 3, so at the last level, that means at the third level, I will get all the horizontal, vertical and detail coefficients, right? So that will be the CH3, CV3 and CD3. And also I am getting extracting the approximation coefficients also at the same level n by this appcoef2 command. And these are actually all commands related to the plotting. And this one, it is for inverse wavelet transform. So WaveRec2 is used, that C and S matrices are passed, the wavelet is defined, and simply you get the reconstructed image IMGR. It is shown here in the different window, right? So let's see that how it executes in MATLAB. So let me jump to the MATLAB. So this program is already written. Let me press this run button. Okay, so let me choose my image. So let me choose this pepper, open, and it is asking me to enter the decomposition level. So I'm entering the 2. Okay, so this is your reconstructed image. And here you can see all the coefficients at the level 2. So approximation coefficient at level 2, you can see it is written there. So these are approximation coefficients and means CA2 at the level 2. These are all horizontal coefficients, and these are all vertical coefficients, and these are the diagonal coefficients. So in vertical coefficients, you can see that all vertical edges are more prominent. So you can choose any of your image. And here you can see some warning. So this is nothing, you can echo off it. It says that that periodization, the signal extension mode is periodization. That's it. It is giving just information. So let me come back to my presentation. Okay, now let's come to the Simulink model. So this Simulink model I have made to decompose one input image into the 4 matrices, I mean the detail coefficients, horizontal coefficients, vertical coefficients and approximation coefficients. And let's see from where I can get these systems. From computer vision system toolbox, you can find this image from file. This image padding is also there. Obviously this image padding is the similar to your image extension, right? Extension mode. So this block is doing the extension mode work. And this is a DWT, I mean it will take the discrete wavelet transform. This is for rotation. Actually this scheme is similar what I have shown you in the beginning. That means row wise and column wise operation. So this is the row wise and column wise operation. Here you can see that image, it is padded. That means boundaries padded as per the requirement to treat the boundary problems, extension problems. And here the DWT is taken. So the row wise is taken, and to take the column wise, the image is rotated 90 degree. And then we are taking the wavelet transform again. So this is the column wise operation. So this is row wise and this is column wise operation. And since your image is rotated, so getting its original orientation, we rotate it again. But this is minus 90. If this is plus 90 rotation, but this is minus 90 rotation. So you get the image in the original position. And this is for image viewer. So you get the output image here. Right, so let me try this in Simulink. And this DWT blocks are actually taken from the DSP system toolbox. So let me jump to the Simulink. This model I have already made. You can see here, and let me show you the angle. So let me double click this rotate. So here you can see that angle is pi by 2, that's 90 degree, and here the angle is minus pi by 2. Okay, so plus 90 and minus 90. And when you open this DWT block, you get you get this dialog. Here you can choose your wavelet. Here I have chosen the Daubishi's 8, and the decomposition level is 1. Okay, the same is here, Daubishi DB8, that is in short called DB8 wavelet, right? And let me show you the image padding, what I have done inside it. So when you open it, what you need to do is the method is replicate. You have the symmetric, circular, and the constant padding. I have used the replicate, and specify. You need to select output size instead of pad size, and add columns to both left and right of the image, and add row to both top and bottom to the image. And how many padding is done? That means to match the next power of 2. To match the next power of 2. Actually, this is a dielectric filter bank. Filter banks are used here for this DWT. So they require the size of input image, I mean rows and columns, in the power of 2. So if image size is not in power of 2, they simply add the extra border to the image, so to make it the power of 2, right? So let me run this model by pressing this run button. Okay, you can see this is my image, this is my input image, and this is the approximation coefficient, this is approximation coefficients, and this is the horizontal coefficients, and this is the detail coefficients, and these are the diagonal coefficient matrix CD. So you can clearly see that how the information is visible. So in this all diagonal edges are more prominent, here all vertical edges are more prominent, here all horizontal edges are more prominent. So that is one level decomposition of image. A reconstruction, I have not made any model, so you can make your own, just do the reverse operation of it. So there will be the reconstruction model also for this image. So this is all about this video. Thank you.